This problem comes from page 404 in Thomas's Calculus. It's problem number 4. Stretching a spring. A spring has a natural length of 10 inches. An 800-pound force stretches the spring to 14 inches. A, find the force constant. B, how much work is done in stretching the spring from 10 inches to 12 inches? How far beyond its natural length will a 1,600-pound force stretch the spring? Okay, well, the first thing I want to notice is this is given to me in inches and pounds, and here in part B, I'm going to be asked to find work. And because I'm not a monster, I want to answer that in foot-pounds, not inch-pounds. I want to use a unit of work that's commonly used that people will understand. So I think my first job here is to make sure all the measurements I use are actually in feet rather than inches. So even in part A, where I'm asked to find the force constant, I'm gonna go on and convert things into feet rather than inches. Now what I've written here is the force is equal to K times X for some constant K. This is Hooke's law. The force it takes to stretch or compress a spring is directly proportional to the amount it's either been stretched or compressed. So I have a spring whose natural length is 10 inches. So the natural length of 10 inches, well, that's 10 out of 12 if I convert it to feet, so I get 5/6 of a foot is that natural length, so that's what I'll be using there. And then I'm told that an 800-pound force stretches the spring to be 14 inches long. So 14 out of 12, or 7/6. All right, so now my job is to find that spring constant using this information. All right, so the 800-pound force must be equal to K times the amount the spring has been stretched. Well, I started at 5/6 and now it's 7/6, so that's 2/6 or 1/3 that it's been of a foot that it's been stretched. Multiply both sides by 3 and I find that K is 2,400. And I always like to remember these constants have units, and that's pound per foot. There's my spring constant, and better than that, I can write down an equation for force. The force is F of X equals 2,400 times the amount I've been stretched or compressed, X. Well, now in part B, I can find the work done by integrating that force function, dx, the amount that it has been stretched. Well, here, how much work is done by stretching the spring from 10 inches, 5/6, to 12 inches, 1 foot? Well, that's 1/6 of a foot. So I'll be integrating from 0, its rest, to that 1/6 of a foot. So let's see. That'll be 1,200 x squared, and I need to evaluate from 0 to 1/6. All right, so let's see, I need to evaluate that, so that's 1,200 over 36 when I evaluate. The 0 doesn't do anything interesting, and let's see, when I reduce this fraction, I get 100 over 3. Units are foot-pounds, or about 33.3 foot-pounds if we wanted to round that to 1 decimal place. That's how much work is done stretching the spring by 2 inches. Because we're not monsters, we're going to use foot-pounds here in the imperial system. All right, part C. How far beyond its natural length will a 1,600-pound force stretch the spring? That's not a calculus question. That just comes to use my force function. So F equals 2,400 times X. 1,600 pounds has to equal 2,400 times X. We just need to do some division. So X is 1,600 over 2,400, or 2/3 of a foot. And since this problem actually starts in inches, maybe we want to tell our reader that that is 8 inches. All right, we found the work done by stretching a spring, and then we answered one more question.